Hi everyone, I'm walking you through a Python script for a soil classification project in Google Colab. The goal of this project is the binary classification of the given images whether they are soil or not. The script uses a deep learning model and saves predictions to a CSV file. Let's break down the key methods, their purposes, the print statements used for feedback, and important points to note. First, we set random seeds with number py and PyTorch to ensure reproducible results by fixing randomness in data shuffling and model initialization. If a GPU is available, we set a seed for it too. The config class stores settings like file paths, image size, batch size, and learning rate. The data is in a shared Google Drive folder. The image size is 224 by 224 pixels, and we train for 15 epochs. The soil dataset class loads images and labels from a data frame, applying transformations like resizing or flipping. It handles missing images by returning a blank image and logs errors, which is critical to avoid crashes. The isTest flag supports both training and test datasets. The findValidImagePath function checks for images with extensions like JPG or PNG, handling inconsistent file naming for robustness. The loadandPreprocessing function reads training and test CSV files with image IDs and labels. It filters out missing images, logs them to missingfiles.log, and splits data into training and validation sets. It prints messages like loading and preparing data, the number of training and test samples, class distribution, and a warning if only one class is found, which could affect model performance. The getTransforms function defines image transformations. Training uses random flips, rotations, and color adjustments for robustness, while validation and testing only resize and normalize images. These are key for model generalization. The soil classifier class builds a model using EfficientNet, B0, freezing most layers to save computation and adding custom layers for our two classes. Dropout layers prevent overfitting, which is important for small datasets. The trainModel function trains the model over 15 epochs, calculating loss and accuracy. It prints the epoch number, training loss, validation loss, and F1 score after each epoch, using a progress bar from TQDM to show batch level loss and accuracy. It saves the best model weights as bestModel.pth based on the F1 score. The evaluate_model function tests the model on the validation set, printing the F1 score and a detailed classification report. It also displays a confusion matrix to show how well the model distinguishes classes. The generate_predictions function creates test set predictions and saves them to submission.csv. It prints generating predictions for test set and confirms when the file is saved, providing clear feedback. The plot training history function displays plots of training and validation loss, plus the F1 score, to visualize model improvement. The main function orchestrates everything: loading data, creating datasets and data loaders, training, evaluating, and generating predictions. It prints the project title, device used, dataset sizes, and a final summary of generated files, submission.csv, bestModel.pth, missingfiles.log, and displayed visualizations, confusion matrix, and training history. Key print statements provide feedback throughout. Loading and preparing data confirms data loading, class distribution shows data balance, epoch updates track training, evaluation results summarize performance, and the final summary confirms outputs. These messages help monitor the script's progress in Colab. An important point: since the data is in a shared Google Drive folder, mount your drive in Colab and verify the folder path. If data doesn't load, check for path typos or permission issues. Set numWorkers to 0 in data loaders to avoid Colab issues. The output shows the script classifying soil images using a deep learning model. It starts by confirming the use of a GPU and loads 1,222 training and 967 test images. A warning indicates only one class is found, which prevents proper class balancing and limits the model's ability to learn diverse patterns. During training over 15 epochs, the loss decreases, and accuracy reaches 100%, but the F1 score is unreliable due to the single class issue. The evaluation skips detailed metrics because all validation samples belong to one class. The script successfully generates submission.csv with test predictions, saves the model weights as best_model.pth, and logs missing files. It also displays a confusion matrix and training history plots to visualize performance. That's the script. It classifies soil images efficiently, with print statements guiding us through the process and robust error handling for real-world datasets. Thank you.